We've now seen how to use conjugate priors to effectively manage uncertainty in model parameters in the posterior distribution, conditioning on data D. For example, for multivariate Gaussians, this would be the mean mu and covariance matrix sigma. I want to also note in passing that with a conjugate prior, you can generally also compute exactly marginal data likelihood. So for example, if you have a conjugate prior to the Gaussian, you can compute the marginal probability of a data set where you're marginalizing over the specific mu and sigma, and instead getting this marginal likelihood. I won't show you this the detailed formula for this, but this is very important and useful, and so just remember that you can compute marginal data likelihoods. But there's a problem that arises when we apply this setup to unsupervised learning where we don't know the categories that individual observations belong to, and I want to spend the next little segment talking about that. So, for example, in the below left case, this might be the case of inferring the phonetic category inventory from a set of continuous input tokens. And we wind up facing effectively a bootstrapping circular problem. If we knew the category parameters, if we knew the mu and sigma for each of the I categories that were underlying this data, then for each datum we could compute the category membership probability. We could get the likelihood conditioned on each category, normalize the likelihoods, and then we would get a posterior probability on category membership for an individual observation. Conversely, if we knew the category memberships, we could use conjugacy to get posterior distributions on the category parameters. But in fact, in an unsupervised learning problem like this, we don't know either one. So we have this bootstrapping problem we have to address. Now, to recast this problem slightly, we can visualize in the following way. So in the upper left, we have the data. In the upper right, we have a directed graphical model, directed acyclic graph, illustrating the generative process underlying the data that is hypothesized. So we'll collect all of the model hyperparameters, the prior parameters, into what I'll call phi. And conditioned on phi, each category has some set of parameters associated with it. So for example, if there are 2 parameters, then we'll have a mu1, sigma 1, mu2, sigma 2. And then within each category, conditioned on that model's parameters, that category's parameters, we will get data that are derived. So some of the observations came in, or the part of the data set which we would call D1, part or D2. And what we don't observe is we don't observe the membership. And we'll call those membership identity indices Z, okay? Now, let's imagine we just assign given number 1 or 2 to each of the observations that we see. We'll call that an observation category assignment. We can score that. So we can break that down into, using Bayes' rule, we can call that the probability of the data given a set of categories Z, which effectively will be how many observations are we generating in category 1 and how many observations are we generating in category 2, times the probability of the number of observations that would be in each category. So there's going to be some prior on how likely, how frequent each category is going to be. So for the first of those terms, the likelihood, P of D given Z and phi, for example, that's where we can use the marginal likelihood that we talked about on the last slide. We're marginalizing over the parameters of the specific category, but we're getting a marginal likelihood of the complete data set. Okay, and so if we can redescribe this a little bit, if we call D sub I as the set of observations assigned by Z to category I, then we can rewrite this as this posterior is proportional to the marginal likelihood of D1, that is the data in category 1, times the data in category 2, and then times that prior of Z given phi. So we can use this at this point, for example, to, if we illustrate one possible assignment Z in this smaller window, so there's blue and red dots, and those correspond to the 2 different categories, this would have a very bad posterior probability, and the reason is that each of P of D sub 1 given phi and P of D sub 2 given phi is going to be very low, because they will be very large categories, and a large category is in general going to assign a bad likelihood. So each of the categories would sort of have to look pretty large like that, and a large category doesn't assign high likelihood to anything, certainly not things that are not close to its center. In contrast, here's another assignment which is going to be a lot better, because you'll be able to, for example, have a category that looks a little tighter for the blue dots, and have a category that once again looks a little tighter for the blue dots. Okay, so that's that's the impetus and the actual math behind how you can score observation category assignments. So you could say, well, let's just search over the set of category assignments exhaustively, and we'll just take the best category assignment. We'll determine those probabilities. But that actually is not computationally tractable because the number of category assignments is exponential in the data set size. So if we have n observations that we're considering k categories for, then we have k to the n possible assignments, and that's not going to scale. So this motivates the idea of Gibbs sampling. So here's the idea, and then I'm going to give you the formal definition. And this is the technique that we're using for the case studies that we're seeing in this lecture. Let's imagine the situation that we knew the category assignments for all but one of our observations, and we'll call that one observation d sub j. Okay, so in that case, it might be this gray observation in the middle of the data set. We don't know whether that's in category 1 or category 2, but suppose we knew the category assignments for everything else. Conditional on the conditional distribution on this assignment, given all the other assignments, is easy. Okay, so for example, we can rewrite this using the definition of conditional probability in terms of two different complete assignments. So we could have the complete assignment Z over where we hypothesize any one of the category memberships for the gray dot, and that gives us the numerator. And then the denominator is we just sort of forget about the gray dot altogether and compute the category assignment probability for all of the rest of the data. And the previous slide allowed us to compute things of the form complete assignment probabilities given data and phi. So we know that we can do this from what we had on the previous slide. Okay, the Gibbs sampling approach is to take this idea and just use it exclusively in stochastically searching and visiting the different possible assignments of collections of data points to classes. So we iterate through all the observations in our data set, and at each iteration, we're going to forget the category of the observation that we're focusing on for the particular moment, and we're going to resample it from this conditional distribution, given all of the other assignments. Here's the formal general definition and characterization of Gibbs sampling. Suppose that there's a joint distribution that exists over a collection of random variables. We'll call that collection X, which is X1 through N. We're going to initialize by just, we're going to initialize a set of values for those random variables. In practice, you can initialize randomly, but sometimes it's more useful to initialize in a less random way. And then at any particular time, let's call in the general case, we're going to go forward a time step to time t plus 1. And then within time step t plus 1, we're going to iterate through the I random variables. So for I and 1 through n, we're going to do the following. We're going to, once again, we're going to ignore the assignment that we had before for x sub I, and we're going to condition on, at every point, because we're doing this from I through 1 to n, we're going to resample that value, conditioned on the current state, the current values of all of the other random variables in the collection. So since we're at point I, and we're iterating from I through equals 1 through n, by the time we get to x of I, we will already have done a t plus 1 time step update for x1 through xi minus 1. And then, but we will not yet have done updates for xi plus 1 through xn. Okay, but as we iterate through this, we will go through all of, at every time step, we'll go through all of the variables eventually. Okay, and if we do this over and over again, one full iteration through the data set is a stochastic update of the representation of x. And so we've changed xt to xt plus 1. And this constitutes what's called a Markov chain on the random variable x. And over time, provided some very general and widely holding assumptions do hold, this will over time converge to the true joint distribution p x1 through xn. So in our setting, this is useful because in many cases, such as this one, it can be the case where it's difficult to work with the full joint distribution, but it's much easier to work with this conditional distribution where we're conditioning on most values for most of the random variables and just dealing with uncertainty in the value of one or maybe a few. In practice, this looks something like the following. So we're going to start in the upper left, and then I'm showing you two iterations, well, within one time step, evaluation resampling for two different of the random variables. So we might choose the first one in the bottom center, and it started out blue, but we might resample it to red. That's actually going to be higher probability because it's closer to the red centroid. And then the second, that might be I equals 1 for a particular time step. For I equals, for then I equals 2, we might choose, that might be this other dot in the left center, which is now gray in the lower left. And that's going to get resampled. Since that's near the center rate of blue, it's probably going to be resampled to blue, and so forth. So this is 2 parts, 2 little visitations of individual random variables within an individual time step. But you will do this for every single one of the data points within an individual time step, and then you'll do that for many time steps. And that will eventually converge, not to a single assignment, but to a distribution over time assignments. So if you take a chunk after you run this for a long time, after a good chunk of time, then the set of time steps that you've got will actually be reflective of, it will be a draw from an arbitrarily close approximation to the true posterior distribution over assignments. And that's how you can use Gibbs sampling in a Bayesian mixture of Gaussians model to do unsupervised learning. And for vowel category inventories, this actually turns out to work fairly well. So this is work of Feldman et al. 2013. So the empirical distribution is shown on the left. And the learned distribution, this is in the first 2 Foreman spaces of vowel inventories for English. The learned distribution you can see is really quite good. It's not perfect. So for example, a and these 2 categories sort of get merged together, and there's not good separation of those and these, but it's really not too bad. And this is the outcome of Gibbs sampling with mixture of Gaussians. So there are a number of limitations that I haven't gotten to yet of this approach. So in particular, I haven't told you about learning the number of categories. There's a very simple idea and picture here that really gives you most of what you need to know for this. The idea is that you want to put a prior distribution over the number of categories, such that you're, eventually you need to have a pressure for fewer categories, because if you're going to have arbitrarily many categories, you can have a bunch of tiny little categories that just fit your data really well. You don't want that. But the general idea is you'll trade off you'll trade off a pressure for fewer categories with the pressure that is intrinsic to mixture of Gaussians models or most unsupervised learning problems, which is that if you posit more categories, you can generally fit data better. So you want to posit enough categories to fit your data well, but not so many that you have an implausibly large number of categories. And Bayesian inference allows you a way of sort of naturally and automatically giving you this. Now, as you saw before, the learned category set still confuses similar vowels. One reason for this is that this model has not taken into account key sources of information that both linguists and probably human learners use to judge whether 2 phonetic input tokens are in the same category, and that's linguistic and extra-linguistic context. So just to give you a really conceptual illustration of this, let's take these confusable vowels in first 2 Foreman spaces, and let's look at the kinds of linguistic contexts they appear in terms of their neighboring sounds. So for example, here's a context which is preceded by and followed by nd. So that in English, in terms of monosyllabic words, is instantiated by the word hand. So a can occur in that context, but e cannot occur in that context. Let's take the preceded by n followed by t context. Both of these vowels can occur in that context. And preceded by fr followed by nd, that cannot be the case for the sound a, but it can be the case for the sound e. So if we were trying to take that information into account, conceptually, we would be trying to learn some kind of clustering according to principles of parsimony, but in order to get a good fit to the data, we would have to distinguish the first and the third context in the sense that not all tokens of this within this class, the a class, can occur in both of them. And that provides some kind of evidence for a distinction between the 2 in terms of phonetic categories on an underlying assumption that there's some kind of regularity of, well, sound categories, members of a sound category generally have similar kinds of instantiation across contexts. That's what it means to be a category in some sense. And so even the linguistic context alone gives you another important kind of information that might help guide you into the inference that these are 2 different sound categories, the 2 different vowels. Extra-linguistic information is even more powerful because in the middle case, there was actually no independent evidence that we had 2 different words here. But of course, they would be used in different contexts because mat and met are extremely different kinds of words. And for example, the word mat is a noun, and it's probably going to be more likely to be uttered in the context of flat things that are on the floor that people step on and wipe their shoes on than the word met is. And so that's going to be another kind of context. And so that will even support a much clearer inference that these are 4 different things. And if they're 4 different things, then it is even more plausible that a and e underlyingly, since they correlate with the difference in meaning, are going to be different categories. So that's unsupervised learning in this continuous space with mixture of Gaussians, and we've covered the role of conjugacy and Gibbs sampling, which is very important and useful in many unsupervised learning contexts.